Oh shit, it's live. Welcome. Welcome to Tell Me More. This is an interview series I have. I'm starting on Mobile Tech Talk, talking to people in the industry about fields they specialize in. So, episode 1, I have the pleasure of having Josh Walrath, contributing editor at PC and this week's all about processors and SoC. So, Josh, just say a little bit about yourself.
All right. Well, my name's Josh Walrath. I'm one of the, I guess the official title is Mangling Editor at PC Perspective. Okay, managing.
That's a cool name.
Mangling Editor.
I just get like senior reviewer, right? That's a cool name.
Yeah. But I've been covering the industry since about 1997, I believe. 3D graphics got me interested in doing some writing and checking those things out. And I started out my own website. I think 1998, wow. And wrote for that for a decade, and then Ryan brought me on in early 2008, and I've been there ever since.
And the website you talk about, guys, is pcper.com. It's a really great website, one I visit every day. They have a podcast.
Oh, so you're the one.
Yeah, I am the one viewer. I am all of your Patreon people. I just have different accounts. So yeah. Did I send you the rundown? I think I did.
You did, yeah.
Cool. So 2015 was kind of a bum year for everyone that wasn't Apple in architecture, in mobile processors essentially. I mean, Intel was doing their own thing, but in mobile, if you weren't Apple with the A9 essentially, and the A9X, it wasn't really a great year for you. Samsung did okay, but they had the manufacturing advantage. Everyone else was on 28 nanometers, and Qualcomm had TSMC's weird 20 nanometer planar that wasn't all that great. So everything bad that happened last year, do you reckon we're going to get a kind of a repeat this year, or do you reckon people have kind of got it all sorted out? I say people, I mean companies.
Yeah, the problems with last year were multiple. First off, Qualcomm, whether they didn't put enough time in or whatever, or they had an internal shuffling, they kind of stopped making their own designs. I mean, there's a couple of ways of making ARM-based products. I mean, you license the ISA and then you build your own processor around it, such as like NVIDIA does with their K1.
Yeah, so NVIDIA does weird things. The K1 and the X1. Oh no,
yeah, the Denver project is essentially the overarching architecture that they're doing. Qualcomm had not the Cairo. Cairo is the newest one, but the Crate.
Cryo's the new one. Crate was before that, and before that they had Scorpion.
Yeah, and I mean, Crate was a really good design for the time, and it certainly outperformed pretty much every other licensed ARM IP, namely the A9 and the A15. Well, at least the A9. I think it was closer to the A15, A16's in that. But, you know, it had good IPC and added some extra features in and made it a really nice product. But I don't know if they were really hoping that 20 nanometer planar would be able to get them by, or if, you know, there was an internal shuffling of what they wanted to do, because I know that they kind of were leaning to go back to just licensing the designs directly from ARM with the A53, A57, and now the A72. Yep. But they may just have started drawing up and thinking, you know, we're not going to be able to get this in time, and so they started working on Cairo. You'd probably want to ask Ryan more about that if you get a chance. He's quite close to Qualcomm. But yeah, Apple had really the only new core out there. They were really one of the only successful guys to leverage 20 nanometer. And there were issues with that process node, namely that you're getting increased size density. So more dies per millimeter square, more not dies, but more transistors per millimeter square. But you didn't get an improvement in power and switching performance. So you've got all these extra transistors in the same amount of space, but it's going to be pulling as much power, if not a little bit more, than a previous generation for that same kind of space.
And the leakage wasn't all that great from what I remember either. It was kind of...
Yeah, I mean, it was very many problems to it, and it was just primarily the issue was the planar design. If they had, thought ahead far enough and thought, hey, let's use FDSOI, we can get away with planar with that and actually have really good performance, they didn't do that. And they thought that this planar on, just regular silicon would be able to do good enough. And it just didn't do it. I mean, Intel had a heck of a time getting to their Tri-Gate, which is their version of FinFET at 22 nanometer. And everybody else was kind of falling behind. But this next year does look a little bit better. I mean, we got the Cairo. Don't know what NVIDIA is doing, but I mean, they're not standing still, but I don't know where.
They haven't said anything about Denver, and it's getting me kind of worried. Because the idea of it, of Denver itself, is a really wide superscalar design. I think it's 7 wide. It's quite intelligently designed, and it's kind of, I can't remember who said it, but this is what would happen if you got a GPU company to design a CPU. And that is what it is. You've gotten a GPU company, NVIDIA, to design an ARM, essentially an ARM kind of based CPU. And it did some translation on the fly. And that was its real problem, is it never really got enough to do to stretch its wings. At least from what I remember. I remember because there was 2 versions of the K1, one with A15s and one with 2 Denver cores. And the only thing we saw Denver in was the Nexus 9 tablet, which had so many other issues apart from just from that. But we were quickly just speaking about 20 nanometer again. I think it's not just TSMC, because there was TSMC and Samsung that both had 20 nanometer nodes, because Samsung did it for their Exynos 5430 or whatever. They did it in the Note 4 and the Galaxy Alpha, I know, for those 2. But again, it wasn't, I think Anantech did a really detailed breakdown of that one, and they just said this is almost terrible.
Yeah.
They just said it wasn't worth the money they put into it, essentially.
Yeah, there just is a lot of drawbacks. And again, Apple is the only company who had, I mean, there are others that have used 20 nanometer planar for their parts. We just don't hear a whole lot about them. I mean, they're limited runs, they're smaller runs, they're things that are not really performance-driven ASICs that we're used to seeing in cell phones. I mean, these would be like, microcontrollers for other products that don't have to have fast switching performance, maybe just have a nice, die size, small, easy to manufacture. But usually when they get to something like that, they'd be rather use 28 nanometer HK metal gate and save some bucks. So, it'd be interesting if TSMC and Samsung would kind of release who used that process and what kind of numbers. I'm guessing that Apple probably by far was the biggest consumer of these products.
The two that I know of is the Note 4 and the Alpha, and both of those also had Snapdragon variants, which were using 28 nanometer, and the Snapdragon variants were sold in a lot more countries. So yeah, with Apple buying space for it, they probably bought the lion's share of either and or both. I don't think they dual sourced that one though. I think that might have just been TSMC.
Yeah, I think it's just the A9X that, or is it the A9?
The A9 is dual sourced, and the A9X is just TSMC.
Yeah.
That kind of moves me on to the next one. So we've been stuck on 28 nanometers for a long time now, and we're not just in mobile either. In GPUs and everything in general. I think AMD put a slide up saying the last real node was in 2011. So it's coming to 5 years we've been on 28 nanometers. I mean, and that time it's gotten it's very mature. We've kind of gotten almost everything we can out of it now. There's not, I mean, there are with Carrizo, AMD got really, really smart with high density libraries to kind of get even more out of it. But 28 nanometers kind of at its edge.
Yes and no. A couple of weeks ago, I wrote about ARM using UMC.
Yeah, I think so.
Their 28 nanometer. They've got a second generation 28 nanometer. It uses a lot of interesting materials. They've done silicon strain, SIGE, all kinds of other things. It's very comparable to what TSMC's very latest third generation 28 nanometer. So if you're looking at process, it's significantly different in between now and when it was introduced. I mean, that just kind of is a logical thing that they would do. And probably they put some of that time that they were thinking, hey, we're going to, further develop 20 nanometer and do that. They probably thought, you can only polish this turd so much before, you're just wasting money. And so they probably split up a lot of the R&D to further 16 nanometer, as well as keep going on the 28 nanometer, because with ARM processors, design is another huge component of it. I mean, really, it's the thing that drives it most. ARM has not been as process dependent as, say, Intel and AMD. Those guys have a lot of guys, a lot of computational power to do efficient place and route, while ARM is a much smaller company. They don't have a lot of the they have to rely on more automation and a lot more kind of smart thinking.
Is that how we're able to see things like the A72 be implemented from like 28 nanometers all the way down to 14 without really many issues? Rather than they're not having to design a core for a certain node, they're able to. Is that? I mean, I could be seeing this wrong, but because they don't have the money to say, look, we need this, only this. If they're able to kind of widen the scope a little bit and have a little bit more, I don't want to say margin for error, but God, words are escaping me right now.
It's okay. My family was yelling in the background, and I lost track of some of the things that you were talking about as well.
There you go then.
So I think ARM does rely a lot more on working with the electronic design software guys to optimize their designs so one, they're easily convertible to other processes, but at the base it's a RISC low power design, and they try to keep things as simple as possible, while x86 is it's the ISA, the original x86 ISA was, a CISC, and then they went to x86 32-bit, which did some interesting things, and then AMD with their 64-bit that got around a lot of the limitations of the x86 ISA. They have to do a lot of interesting things to get good performance. I mean, they've had register renaming for ages. They've got the macro ops, so you've got the decode front end, turns it into kind of a RISC-like processor on the inside with the execution units, and it all conforms to x86. And Intel's got all kinds of guys doing hand, place, and route. These engineers that spend just ages on what would be kind of simple circuits that this EDA software would be able to place in like a week. It'll take an engineer, a month or so. It just is very time consuming, and that's why Intel is able to get the IPC, the power, and all these other things out of x86, which is not designed from the get-go to be a low power architecture. But ARM does not have those resources. They don't make $15 billion a quarter.
God,
that Intel certainly does.
That many zeros makes my head hurt. Like that's a lot of money.
I know, and I mean a good quarter for ARM is maybe 500 million,
something around that.
But then consider that they only sell licenses. That's that's a
they
lot of
don't do
that's good
any actual
royalty, and
manufacturing themselves.
yeah, so they don't have to worry about any of that stuff. They just kind of help their partners get things to market. So
that kind of sorry, Karen.
go ahead.
No, I was going to say, so that kind of moves into the next part of the question. So this year we're seeing, Samsung's second generation 14 nanometer, their LPP or low power plus, and TSMC's 16 nanometer FF plus or FinFET plus. They're both second generation FinFET nodes. I think nothing ever shipped on TSMC's just standard FinFET, did it? They kind of iterated very fast and went to FinFET Plus.
I can't say that they didn't. I imagine they did, but these are going to be again for customers with very special
very
needs,
low volume
customers that are not going to have a huge amount of volume, and they're going to sell line space, and it's probably going to be still expensive to do that. But I think it's a balance between developing and making sure that you have a usable line, but also having consumers that are willing to take risks to make these wafer orders, and probably there's some real serious contract negotiations about per good die and yields and bins, that if TSMC does not hit these benchmarks, then they probably end up paying less and less, and these guys, they don't talk about these contracts at all. We have no idea. TSMC's closed mouth about it. AMD, Apple, whoever. But there's something out there, obviously. But FFP is going to be their big seller that they're hoping is going to truly eventually replace 28 nanometer HK Metal Gate.
Okay, so we know these are the two main ones that are kind of coming in from here on out for the foreseeable future. I mean, only I think Intel and maybe TSMC have like 10 nanometer on the horizon, and they have like rough dates. But for the foreseeable future, we've got 14 and 16 from these two players. I discount Intel because aside from like a really weird deal they have with Rockchip, they're not really manufacturing ARM processors.
Yeah.
So, I mean, I kind of know, but I want you to explain to it. How do you think moving to these much lower, much smaller, nodes has helped with SoCs, especially in mobile?
It's gonna have to really depend on the design. For watches, low power stuff, things that do not require a large SoC, you're going to still see a lot of guys leveraging 28 nanometer, this third generation stuff. Things that you don't have to have the most amount of performance out of there. Another option is 22 nanometer. Oh gosh, what is that? Global Foundries. It's X.
FDX.
What?
FDX, I think.
Yeah, I think you're correct, and that's their fully depleted SOI product that still uses planar. I think that there's like a 28 nanometer metal backend that they're using, but everything else is pretty small. So they've got the benefits of higher density and using FDSOI, and I think it's back bias that their leakage, but is really low. However, their high performance is not horrific. So it's a nice combination. However, it's only one group is doing this, and it's Global Foundries. It's brand new, and oh, good. Apparently, my child is having a fit, and my wife has slammed the door and run off. But anyway, yeah, Global Foundries is the only person who does the FDX. And we don't know how many wafer starts a week that they're going to be doing to this. It's a brand new process. And this is something that I think is probably going to be in a lot of wearables. And they're aiming for IoT type stuff. And anything that they can do to improve battery life without having to have, you don't need a huge amount of performance for a lot of these things. They're going to jump on that. If it's a really small design, 16 and 14 nanometer may not be appropriate.
I think I remember you saying on your UMC article, like trying to get like an A7 on 40 nanometers, it's so small that it might not. It's possible. I mean, Samsung's done it, but it's getting. There might not be enough surface area left to place it.
Yeah, because how you've got multiple levels on any chip. You've got the substrate, and then you've got the die on the substrate. Now, the substrate has got all the pins and the FPGAs, and on the bottom of the die are a bunch of pads that you've got to nicely mount that on top of the substrate so that the pads go to the correct pins on the bottom of the substrate, and they can be, more effectively and easily mounted on any kind of surface mount PCB, such as either your cell phone and sorry about that bang.
No, it's fine.
And anything else like that. If you've got like a dual core A7 with very little other extraneous supporting hardware, like a very simple GPU on that, very simple I/O, you might not have enough die space without actually kind of inflating that naturally and kind of wasting space to be able to get as many pads on there as you want. And that then doesn't make sense, because here you've gotten this advanced process to try to squeeze as many die per wafer out and get all these power advancements and maybe performance. And the next thing you know, you've got to kind of inflate your die size and maybe put some empty spaces in there just to get it to the size where you have an adequate enough pad count on the bottom of that so you can mount it to substrate.
Yeah, I'm just
so it's a lot of balance. What's that?
No, I was about to say, I was just having a look at something ARM announced earlier today, the Cortex A32, which is an A35, which they announced a few months ago, with essentially 64-bit support chopped off, so they can get it even smaller, even lower power. And it is 0.25 millimeters squared at its smallest configuration, and that's less than 4 milliwatts at 100 megahertz, which is kind of staggeringly tiny.
Yeah,
I don't really know what to say. It's so
yeah, it's very efficient what they're able to do. I mean, if you consider the amount of performance you get out of a 500 milliwatt part, such as most cell phones are kind of in that area, and they're running anywhere from 1.5 to 2.4 gigahertz, depending on the SoC and the process tech. Yeah, you can get those things really tiny, and if you look at their really low Cortex M, which can run on one of those little motherboard batteries for like 7 years.
Yeah,
I mean, it's mind-boggling what they can do. And again, products like that are not as dependent on process node, because it's a lot of design work. You don't have a whole lot of extraneous things. You don't focus on performance. You don't have to throw all these extra transistors to increase your IPC. Hey, let's double our die size and get maybe 4% improvement in IPC and overall performance. That when you're hitting that limit, then
for the people that don't know, do you want to say what IPC is? For
instructions per clock.
Yeah. So it's just essentially what it can do in a certain amount of time.
Yeah. And so when you're pushing against IPC and trying to get as much performance as possible, then these process node changes are absolutely key, because you can easily double your transistor count. You can get that better performance. You can add more features to there, and you're not going to be increasing power dramatically from the previous generation. In fact, you may see an increase in efficiency depending on where you're at with that node and how you kind of handle your design.
Yeah, I think that's kind of what we're seeing with both AMD and NVIDIA with the upcoming GPU releases. They're both touting like 2 times performance per watt.
Yeah, and this is going to be by far the biggest jump that perhaps we have ever seen. The only thing that may be comparable was going from the Voodoo 1 to the Voodoo 2.
See, that's before my time. So this is like kind of, for me, this is probably the biggest jump technologically that I will have witnessed in technology. This is exciting for me, because it's so intricate and exciting, and we saw like Nvidia do some incredible stuff with Maxwell when it came out, and just how much more efficient it was than Kepler on essentially the same node. Again, there are, like you said, there are improvements between generations, but like Maxwell was so much more efficient than Kepler. And to a certain extent, AMD had a similar thing with oh Christ, what's it called? Tonga and
Tonga versus
Tahiti. Yeah. So this is something going like physically shrinking for like AMD. It's in half. Like essentially, it's
this is kind of the perfect storm of where we're seeing these products come out. So about 10 years ago, I wrote a editorial called "Slowing Down the Process Migration," and this was back in the 250, 180 nanometer, going down to 90 nanometer days, and how even back then we were starting to see kind of some slips in time, and how much more money was being spent on fabs to go to each new process node and R&D and the things that they had to do in terms of research with materials and metals and deposition and going from single exposure to dual exposure, lithography, immersion lithography. And essentially the final point in my argument was that these guys cannot lean on process node advancements to make better and better products. They're going to have to invest in engineers to actually rethink designs, make things better, and go more from the ground up instead of just relying on these advances. And we've seen both AMD and NVIDIA do that. And certainly when we went from Kepler to Maxwell, we saw a huge jump. And they leveraged what a lot of the things that they learned with Denver and low power and ARM architecture, and they put a lot of that DNA into Maxwell, and they're going to continue that along with Pascal. So not only are we going to see a huge jump in performance just from the process node, and I mean that's going to be a true doubling, maybe a double and a half of transistor density from 28 nanometer in these 14 and 16 nanometer products. And with FinFET and things, again, that TSMC and Samsung and other guys and the litho guys have all done, we're going to see some better power consumption as well in terms of, performance, wattage per millimeter squared and depending on switching speed. And it's going to keep a high switching speed, but we're going to see easily, SLI 980s in a single card, if not maybe a little bit better.
I think I'm trying to remember back. The 980 at launch was around the same time as the 290X, wasn't it? Because it was before the 390 had been introduced.
Correct.
So the 980 at full whack is only about 185 watts, isn't it?
Yep.
And the 290 was at what, 275?
Yeah, they said 275, but it may have been a little bit higher. I think that some people were considering it was an easy 300 watt part. But again, that also goes to show what they've done with 28 nanometer process in that time, and also what AMD has done with just some basic redesign work on that chip. They turned that 290X into something with 390X that is faster, but is now a true like 250 watt TDP part.
And it kind of annoyed me when the 300 series came out and people said it was a rebadge. It kind of was, but the chips were respawned, like you said, they were redesigned to be a bit more efficient, a bit cooler, which was a big thing with the 290s, that they were hot cards. Like 1995C, like pretty much all. I mean, the stock coolers were terrible,
Yeah.
but they'd done some smart engineering in between to do it better. And again, I think that comes down to what I'm trying to say is when you can't rely on, like you said, on fabs every 18 months, 2 years getting better. You have to design smarter. You can't take it's not easy, and I know it's definitely not easy, but it's almost like taking the easy way out when you know you're going to get an X amount decrease in wattage and X amount increase in space per wafer because it's shrinking so much.
Yeah.
When you say like, look, we're going to be stuck here for a while. We are marooned on 28 nanometers. We've got to get smart. And like I said, we saw this with Carrizo and Excavator compared to Steamroller. I can't remember the exact number, but it was they did a lot of like impressive stuff to get the size down, the heat output, the power consumption down.
And a lot of that is they've redone a lot of the power gaining. They've redone a lot of power distribution, and they're really, really aggressive on downclocking parts that they know are not going to be utilized and able to actually quickly clock those back up when they're needed. And so you've got portions of the chip that are just going on, off, and that in the end, over time, lowers your TDP. It's going to lower the heat output. It's going to lower, the power needed. And this was then kind of the thinking transferred to the GPU guys. And then at the same time, you've got the GPU guys with high density libraries going to the CPU guys and able to kind of mix and match the stuff that really works well together and accentuates the positives of whichever architecture they're working with. So yeah, this 16 and 14 nanometer stuff coming from AMD and the Polaris and the Pascal, it's going to be a lot of fun to watch. I think it's going to be really exciting, and hopefully we're going to have a few more features added in, certainly with DX12 being at the forefront and now Vulkan.
Yeah, that did a couple of days ago, didn't it?
Yep. Yeah. So it's going to be very interesting to see how each company has embraced some of these new technologies and what they're planning on doing with them in the near future. But the rumor is in April for at least some of the AMD 14 nanometer parts.
Yeah, the mobility parts, isn't it?
Yeah, don't know if that's true or not. Take it with a grain of salt. I was thinking more summer, but definitely Pascal by the end of summer, I think.
Yeah, I mean, from what I remember, again, I've been in this a lot less time than you have, but from what I've seen, I've essentially seen from 60 downwards, maybe like closer to 45, but kind of jumping down nodes is, from what I've seen, been kinder to AMD than it has been to NVIDIA. I mean, NVIDIA seems to have, especially with DX11, they'd had way better drivers, but it kind of been like when it first came out, I think. I mean, again, I could be remembering it completely wrong.
No, I mean, yeah, I think you're right, because the GTX 480 was not a great card. What do they call it? The FX50, not the FX, but God, why can't I remember the AMD
Radeon
5870, the Radeon 5800 series, 5870 was their high end.
5970, yeah. Sorry.
Yeah, and that was, that as compared, that was a great card. Pulled down less power, was just as fast, if not a little faster in some things, and they could keep the price up there because those Bitcoin guys really seem to like those cards as well. But you kind of wonder if cross-pollination from the CPU guys, as well as perhaps some expertise and some of the software that they're using for design and layout, that they've handled the process node jumps, a little bit better. I mean, they were the first out with 28 nanometer, but NVIDIA wasn't that far behind with Kepler and 28 nanometer, and they did a much better job with that than they did with the old Oh, the GTX
Firming?
480. That was a hot monster.
Hot being the operative word.
Yeah.
So I kind of want to transition into this next bit. So we've been speaking a lot of numbers. So 28, 22, 20, 16, 14. But something we've been saying a lot about is FinFETs. So kind of from like a high level, kind of, do you want to explain to people what a FinFET transistor is essentially, and what its main advantage over
Goals are
planar is?
okay. So it's essentially a design structure where you've got the source and the drain, and in between there is a physical gate that is made of a dielectric material, I believe, and then you've got the connection between the source and the drain. The gate surrounds that entirely. Now with planar, they didn't have any of these 3D structures, so you've got the wire leading there for the drain and source, and then you've got other materials kind of around doing strain and either compressive or expansive, and then some other materials in there, and then you've got the source and the drain. But a lot of that causes leakage around there just because of the way the design is. The electrons can kind of push through these areas, and this is something that SOI helped with a ton because it was a much better insulator and didn't allow nearly as much leaking at the gates. Now with FinFET and the way they've designed it, it's actually an SOI layer, but they're using regular silicon wafers, and then they do a deposition of this SOI. It's different from what the PD and FD-SOI guys make. Soitec is the wafer manufacturer who specializes in that, but it's still essentially the same kind of material. And then they put source, drain, and the connection and the gate all on top of that. And there's also, I think, a lot of air in between there. Eventually, I think they kind of fill it in with other deposits, but it cuts down leakage really dramatically without affecting transistor switching speeds. So it's kind of a win there. I mean, they're not gaining a whole lot in switching performance, but they're gaining a ton in the amount of leakage that they've cut out. So it's
also where we get the fin name, is these 3D structures.
Yep.
They resemble like
gate,
shark
source,
fins.
and drain. If you look at the diagrams, I mean, they look like these fins that are standing up in the air. But yeah.
And this is kind of the interesting bit for me, because how I originally came to think up this interview type scenario is actually around this next question. So is FinFET the only option? I mean, we've spoken about how we've come from planar. This is kind of the next big thing, but like you said, there's FD-SOI, fully depleted silicon on insulator, from Global Foundries, but you said it's only them. Like, we don't really know how many wafers they're making a week. We don't know how many contracts they've gotten.
Well, SD Micro and Samsung both have a 28 nanometer FD-SOI. SD Micro is going to be a lot smaller with what they can do. Samsung can ramp theirs up if they've got their fab set up to handle FD-SOI, or at least these certain lines, because there's some issues with cross doping wafers. If you're running FD-SOI and then you try to run a regular silicon wafer through that, you're gonna have problems. It just doesn't work. Physics is a bitch, and especially materials physics. It can be really, really cranky. But FD-SOI and FinFETs are not mutually exclusive, just because FinFETs are based on silicon on insulator technology. So perhaps with FD-SOI and FinFET, you can get maybe a little bit more cooperation between the materials to have slightly better leakage than just FinFET with its thin layer SOI, as compared to using a fully depleted wafer. And I could be confusing and mixing up these things. I've had things explained to me a bit, but I'm sometimes a little thick and dense, so I'm doing the best I can.
I mean, from how I understand it, because like I said, the way I came up with this is I was researching FDSOI, because I find it absolutely fascinating that the planar FinFETs. I find all of this like because I never feel like I know enough, and this was kind of like the new hotness. So I was like, oh, like there's almost nothing about this. I need to know more.
Yeah.
So basically, what I understood, or which again could be completely wrong, is it essentially gets the leakage levels down to FinFET levels, but with a price closer to planar levels. So you kind of get the best of both whilst being in between. Um, so at least on their 22 or Global Foundries 22, they said it was kind of power level similar to TSMC's 16, whilst being closer in price to their 28.
Yeah,
So
I think with a gate last design, and I think Global Foundries is that they're probably improving upon FinFET at 16, and certainly it's an improvement upon 22 nanometer FinFET, the older version from Intel. And yeah, you're doing it with planar type um, designs, which are easier to implement. I mean, it takes time. It takes some really interesting masks and everything to get these 3D designs to actually be built up and work properly.
yeah, I
And
think it's ST Micro said they can essentially port. I think it's like 90 or 95% of uh, the fabs. It's like the last 5-10% has to be essentially tweaked.
Mhm.
We can't underestimate how big that last 10% is. That's
Yeah,
still a huge undertaking, but
yeah,
it's not a ground up rebuild. Is what I'm trying to get at here.
yeah. I mean, you're still going to have to design to the electrical characteristics and design rules of that process node. I mean, and each one's going to be different. Yeah, they borrow some things from previous. In the case of ARM, they're actually taking some FinFET design rules and not actually migrating the structures, but some of just the layout rules from the 16 and 14 stuff and applying it to 28 nanometer and getting better results in what they're doing in terms of density and performance. Yeah, I think, moving forward, it's all going to be FinFET until they find something else that they need, something else. And there are those who think that 10 nanometer might be the last FinFET, and they're going to have to do something like quantum well type designs, which I have absolutely no idea. I mean, I've
Yeah,
heard the
no,
word,
that's
no idea how it works, if it even works. We've also got some of the first EUV litho production going on now.
I was
I
just about
actually
to
have
say
a
about
friend of
that
mine.
stereolithography going with ultraviolet instead of
Yeah, I mean,
can't
the
remember what we're currently
industry
using.
went 100% and bet the pot on EUV, and it's finally
Paying off.
starting to work. Um, and yeah, a friend of mine actually works for, I used to be ASML, and I can't remember which group it is now, but he went over to Japan and implemented a EUV 100-watt litho machine for a Japanese company that is starting a lot of their testing, and it'll probably go into production sometime next year. But the machines are being installed in the fabs, but it's going to take a while for those to be fully integrated and fully working, and all of the physics around the actual implementation and how that applies to transistor design. These things are going to be a lot of work from but yeah, we've I think Intel, and this, we can kind of go into this, TSMC and Intel saying 10 nanometer in 2017. I think TSMC is going to be farther than that, and I think Intel with 10 nanometer is going to be very, very similar to what we saw with their introduction of 14 nanometer, in that there were very few parts. They still leveraged and really leaned upon their last generation stuff with the Haswell and 22 nanometer, just because process technology is hard, even for guys with billions and billions of dollars. So yeah, we may see a couple of parts come out in 2017, but that is still another big jump. I mean, they're talking about what is it, triple mask
Yeah,
lithography.
I think Intel especially is kind of like, look, this is getting hard even for us at this point. They're stretching out their TikTok kind of thing, so it's TikTok, or it's
Yeah.
iterate, refine, refine now instead of iterate, refine, iterate, refine. So yeah, I've heard similar things. It was like 10 nanometers, or like at the very, like at the most stretched it can get like 7, and the 7 is like pushing the boundaries of like silicon itself.
Yeah, I mean, we're going to have to do some really interesting materials, and because at 7 nanometer, we're starting to talk about dozens of atoms
Yeah,
in a in a source or a drain.
like I
It's
said,
just
physics is a bitch.
it really truly is when you're getting to that point. And who the heck knows what they're going to do. I mean, lasers and light and photons and quantum effects. It's going to be interesting what they do with design to try to keep up, because process technology, we're going to be hitting some big walls in the next 10 years, and I really don't know where we're going to go after 2025, 2026. Just in terms, I mean, we're going to be having 5, 6, 10 atoms per transistor. I mean, just how do you control that?
Um,
How does you keep
I'm
that
still trying to wrap my
coherent?
head. I'm trying to still wrap my head around the fact in the last decade we've gone from 90 to 14,
Yeah.
which again is, at first you're going like 15 nanometer drops to 10 nanometer drops, 15 again, and it's just it's when you see like pictures of it, it doesn't quite sink in until you see like actual dies. When you see the size of dies like shrink between generations, is when it kind of sinks in.
Yeah, when I first started paying attention to it, I mean, Intel was really proud because they broke the micron barrier. So they had the one micron processors, which I think were 486 designs, and then the Pentium was like 750 nanometer, the original, and then their later versions were 500 nanometer. But of course they called that 550 micron.
I'm trying to think, is it the 386 or the 486 that AMD kind of reverse engineered from a photo?
It was the 386, and they didn't reverse engineer from that. They Intel used them as a second source for 8088, 8086, and 286 processors.
Oh, okay.
And so then they also second sourced them for 386, and that's when they kind of AMD started tweaking and releasing their own, and then they had their own 486, and then 586, and finally the K5.
Okay.
So yeah, it was. Go ahead.
Oh no, I was about to say, like, we kind of got back onto AMD again, and this kind of transitions quite neatly into my next one, which is more about GPUs. Especially, this is a much shorter time frame. I'm speaking of the last 5 years or so. So, God, it doesn't even seem that long ago. We're talking about like iPhone 4 onwards and the first Galaxy S onwards.
Yeah.
Up until now, and it's the last 5 years, like GPU companies have kind of gone insane on especially in mobile, because again, like they have to get clever. They can't draw too much power. They can't be too big. They can't like just do too many calls or anything. Who do you think has done the most? Because we've seen like Nvidia kind of came into it in 2011, I think, with the Tegra 2, but that was lacking in many ways. We had Imagination Tech doing a lot of stuff, who were kind of big around and then kind of faded for a while. And I think the only people they really give, they don't give it away, but Apple is the only real people I know at the moment who license Imagination's GPU. Mm-hmm. But we've got Mali and again, like GeForce from Nvidia. Who do you think's kind of done the most?
Nvidia kind of came in with a big splash, and a lot of people were expecting a lot of really interesting things from them, and they've done some neat stuff, but their pickup has not been nearly what they were hoping and certainly expecting. And so I think that they have focused more on their bread and butter, which are desktop GPUs, as well as getting into the server spaces. And now I think a lot of their push is going away from mobile and doing more of the the deep learning and going into automobiles where TDPs are not nearly as important. You saw that big brick thing that NVIDIA showed off at CES that has to be water cooled.
PX2 or something. It's like 2 Pascal GPUs, a ton of CPU horsepower, and like you said, it has to be liquid cooled.
Yeah, and so they've gotten away from the cell phone because those things are low margin and something that they were not used to competing with. And I think when you finally got to the bean counters, they probably thought, you know what,
it's not worth it.
We can utilize this engineering talent to produce parts that have margins that were 4 to 5 times higher than what we'll do anytime in mobile. I mean, certainly we're going to keep a presence in there with the Shield stuff, but they're just not pushing it nearly as much as you would expect, just because, I mean, they got a ton of competition in those places with Samsung, ARM's other partners, all these Chinese firms that are kind of coming up, MediaTek, people who are willing to sell stuff at extremely low margins, which, NVIDIA, they don't have to. They can aim those engineers at other projects that will have 3 to 4 times the margin of what these SoCs have.
And I think it's important to say, like, at one point they were very interested in mobile. They bought a company. They bought Icera, a software-defined modem company, and they recently wrote that off and kind of sold what was left of it, didn't they? And that was like super interesting. But I think only one SoC, the Tegra 4i, actually implemented the modem.
Yeah.
And there was one of the Shield tablets had a 4G version with the Icera modem that had so many problems, but it just couldn't hold on to anything.
Yeah.
But yeah, at one point they were very interested. And like you said, they weren't almost used to competing this much and for this little money. And like you said, mobile is very constrained in many ways. Like, there are thermal constraints, and you will not get the margins you'll get on a desktop GPU.
No.
Or I don't know what it's like in server space, but selling X amount of.
Yeah, and there's no market currently for ARM server products. I mean, there's a small one, and people are starting to explore that, but it's still nowhere near what NVIDIA can do with their top end Tesla gear and all their server based things, which have margins that are just out of this world, and everybody would love to be able to make that kind of money on
orders of
on products. Imagination has, what's that?
I just said it's orders of magnitude higher than what they were getting in this.
Yeah. But Imagination has done some interesting things with their graphics. They've stayed relevant even after kind of abandoning the 3D world in around 2000 2002, and going straight to mobile. And then they're competing with, Adreno from Qualcomm, which Adreno used to be ATI.
Radio. Yeah.
But I think the people who we have seen really the most traction from and the biggest jump in performance and features is got to be the Mali guys.
Yeah.
I think ARM thought many years ago is like, hey, we've got to be able to. I mean, this is the original iPhone and the graphics on that and the things that it was able to do. I mean, they probably thought, okay, we've got to get up to speed. They hired a bunch of people, and they seem to have decent licensable products. I mean, certainly I think Adreno may have a performance advantage just because they've been at it longer. They have a more historical graphics design team, and they didn't really have to start from scratch. But going from A to B, the Mali guys really have stepped it up, and they have some solid parts and good technology, and they're part of the HSA group, and they're not unwilling to explore interesting avenues. So they're really kind of at the top of the game. They may not be, the best performance in terms of, pixel throughput and power, but they've come a long ways.
Yeah, I think the last generation's high end was the T760 with up to, I think it was up to 8 clusters, which is what Samsung used in the S6, and it was very close to what Qualcomm was doing in the 810. But as you said, having the background that the Adreno guys do have, like I said, they were spun off from ATI's Radeon group. So that they have, their background is literally graphics. So that, and they kind of have the pedigree there, but what Mali's been able to do, what the Mali group has been able to do in such a short amount of time is nothing short of amazing. And if I remember correctly, you had an interview with them a couple of months ago or something.
Yeah, Jen Davies.
Yeah.
He's an interesting fella.
And again, ARM is one of those companies I could speak about for ages, because they're not the typical, like, we make things, you take this, and we make money. It's, we design it, you can like license it from us, you can also tweak it yourself. Like, we also make graphics, we also make microcontrollers, and wherever you're really looking, we also have a design for that. Yeah. So ARM is an interesting company.
Yeah. And I mean, they had a lot of years where they were not really making money, and they were kind of scraping hard, where their quarterly results were pretty. I mean, they barely lost money, but they didn't make cash. And it wasn't really until the last 5 years that we started seeing them. And I think that's when they've been, obviously investing more in engineering, partnerships with the software guys, and for design, and plus they're, implementing their POP, which if they can get their products faster to market, then that's fantastic. Because I remember many years ago,
it was like 18 months from like announcement to when you'd actually see it somewhere.
Yeah, they'd announce it. It's like, well, when do you expect this? And this was like 2010. It's like, well, we expect to see it early 2012. It's like, why are you announcing this now?
Yeah.
We're so used to the NVIDIAs and the AMDs and the Intels of the world who just pop out of the stuff and release it. And a couple of weeks later, we got products on the shelves. ARM, is taking the very British attitude of, we're going to have tea first.
As someone who's just
we'll ship it on our time.
I can't really say anything. But yeah, no, it was very much kind of taken at a leisurely pace.
Well, it wasn't leisurely, but they just announced it so early because there were so many steps in the process to be able to get, okay, you design this, then you license it out. And those guys who license it out still have to harden the design. They got to do things to address whatever process node that they decide to use and get that thing into production and debugged and reach optimal yields and bins. And that would take the longest time. They get the design down, getting that into production was a chore. And this is something that their POP has improved upon, and plus their partnerships with the actual foundry guys to get the design, the initial implementation to work on as many process nodes from different vendors as possible. So these are good things.
Yeah, I don't actually know this. What does POP stand for? Because originally I thought it was package on package, but that's something else.
No, that's ARM POP. I can't remember. The POP IP,
it doesn't matter.
physical. What is it? Do.
Whilst you're looking,
I know.
I'll tee up the next one.
I cannot remember exactly what it stands for. It's processor optimization, physical, whatever. But yeah.
Yeah. So, like we said, ARM is a very interesting company, and we're seeing a lot of companies, a lot of companies nowadays take the route of getting an architecture license from ARM. One of the most famous is, of course, Qualcomm. Like you said, they had Crate, Crate was a knockout. I think when Crate came out, it took everyone by storm. Like no one expected Crate to be as good as it was because Scorpion was actually kind of terrible. So they were like, yeah, they're trying it again. Let's see what happens. And then it turns out that, whoa, 2 of these Crate cores is actually equivalent in performance to 4 Cortex A9s.
Yeah.
And it's like, oh crap. Essentially that was it. And for the longest time, it took a lot of companies to recover from that. And the A15 was behind schedule. The A15 also consumed a lot more power than they thought it would originally. And again, Qualcomm was just like, yo, we got Crate. You can have 4 of them now. I remember them when they did the S4 Pro, and it was the first quad-core Crate. Because for so long, they were beating the drum of like, 2 is enough. And they were like, look, performance plus. And everyone just went nuts. Then
Apple came along with their unique design and kind of redefined what performance on ARM is as well.
Exactly, and Apple is another one where they started off taking licensing standard ARM cores. So they did A9s for the Apple A4 and I think A5, and maybe the A6. I don't know. But afterwards they started designing their own. So we've got Cyclone, Typhoon, Twister. We can see a bit of a naming scheme here. And as we spoke about earlier, NVIDIA also has an architecture license with Denver. AMD even has an architecture license for ARM at this point.
They're doing the K12 in 2017.
So what is an architecture license from ARM, and how does that differ from the licensing that we've been speaking about previously?
Okay, now say that again.
How does the architecture license from ARM differ from the standard licensing model they show?
Well, I mean, they're licensing out the ISA, and it's I guess a fairly decent comparison would be Intel licensing AMD the x86 and AMD relicensing x86 64 to Intel. They get the ISA, they're covered legally that they can design their own chips using this ISA and paying the royalties because they didn't develop themselves, and they can do unique and interesting things with the designs. So yeah, licensing the ISA is more money, but the rewards can be greater as well, as we saw with Qualcomm. If you design a product that is significantly faster than what the competition is licensing directly from ARM, then that's going to be a win for you, because you're going to have better battery life, you're going to have better performance, you're going to have better thermals. If you kind of hit the sweet spots in all design and process, and you can beat up on your competitors like that. But it's expensive to do, and you've got to have a lot of engineers. You got to have a lot of engineers, and you got to have some guys that know our architecture in and out, and they've got to be familiar with everything previously, the drawbacks of previous designs, things that perhaps they implemented in other designs that worked really well but just didn't fit in with the rest of it. I mean, it's like Jim Keller was a big deal at Apple.
I was just about to say Jim Keller. He's kind of the iconic person who he did some great stuff at AMD. When he was done there, he kind of up and left. He ended up at Apple for a little bit, and he did the A4 and the A5. And then after that, Apple kind of was like, look, we know what we need to do now. Came back to AMD, did Zen. He's since left again. He's now at Tesla. So yeah, you need some very smart people to design your own core.
Yeah.
So yeah, thank you for everything. And I kind of want to tie this off before we run too long.
Excellent.
Is there anything that's been kind of announced but isn't shipping yet that has you excited? So for me personally, it's a tie-up between something I know is coming very soon, which is Cortex A72 and A35 combination, so like big little. We know they're coming. Like they've been announced. We have to wait for them. We've seen A72s already. We're going to see A35s soon-ish, and I kind of want to see them I really, it's not going to happen. I really want to see like one A72 and then one A35 in a big little mode and just like do it that way. But no one's going to do that because more cores equals better according to most people. But Soft Machine has their VISC architecture, their virtual instruction set. Because basically, from the way I understand it, is if you have like 4 physical cores, you can make it think it is one just very wide core. So that has me excited. Is there anything you're excited for that's kind of been announced but is not out yet?
Oh, geez. Well, boy, on the x86 side is going to be interesting. I got to readjust my lighting here because this white is just blinding. Oh, that's much better. Zen is going to be interesting. That's going to be a make or break product. But everybody's looking to that. When I was briefed on A72 quite a while ago, I had talked to some other people around the industry, and they thought as well that this could be a watershed product for ARM. This could get over some of these performance and other issue bumps that they've struggled with through their entire time, just because of having a low power architecture and the trade-offs that you make to get there in terms of just data flow throughout your product and how it executes software and gives you results. A72 supposedly is really a significant jump in overall performance and efficiency than everything that they have done before. So I'm interested in that. And of course, 16 and 14 nanometer graphics is going to be very exciting, and that's probably what a lot of people are going to be focusing on for the next 6 months.
I mean, as an AMD fan, I think I'm also very anticipating Zen to knock my socks off. And like you said, it kind of has to at this point. I've just kind of retired a Phenom 2 X6 build. I kind of side graded to an AM1, a 5350. But it's weird. It's lower cores, like lower amount of cores, lower frequency, and it's obviously not as fast. But it's got the much better GPU, and it does some HSA-ish stuff, and the OpenCL performance is way better than what it was. So it's kind of a side grade, but it's 25 watts compared to, I think it's like 95 or maybe 65 for the Phenom 2, and it's like, the fans aren't running all the time.
Yeah, the Phenom 2 is it's 125 watt part.
Oh, damn.
Yeah.
So a bit higher than I thought it was. So like you said, Zen kind of has to be is definitely a make it or break it part.
Yeah.
I kind of shied away from Intel here. I don't know why, because they are trying to do mobile. That's all I really have to say about it.
I got a hint from Francois Pidonal. He's a engineer kind of high up in Intel. Said, watch mobile in 2017 with Intel. They've kind of promised us that before, and they've kind of
Moorfield, Medfield.
Yeah, they just have not been successful with it. I mean, especially as compared to the ARM stuff, and they work fine and they kind of hit some of the power things, but it's never taken off. They've never had the advantages in terms of software and partner support as ARM has obviously had. And until you get a product that is so much better at everything than what is currently available, you're not going to break into that industry unless you, as they did, they essentially gave the chips away for free.
Yeah, that was kind of my issue with it, with Intel doing mobile, which is you're using your dominance somewhere else, and like there is no doubt they are definitely dominating the desktop and higher end mobility, so laptops and stuff, to essentially fund their mobile. It's like, look, like they can give these chips away to Asus, to Acer, and everyone, and say, look, it doesn't affect our bottom line that much. Just take it. And then when you essentially saturate the market that much, it's like, well, look, why won't we use this? Performance is good enough.
But they've never gotten quite over that hump yet.
So I think I'm gonna. Oh, sorry, I was about to say. I think
one last thing. Do you remember back in the? And speaking of VISC. Do you remember the Crusoe processor?
It sounds familiar, but I don't want to give you anything concrete on it.
Okay, well they used something that was kind of similar in that they took x86 and they converted it into something really so totally different in the software layer. And Denver did much the same thing. What?
Is this the transmitter stuff?
Yeah.
Yeah, yeah.
The transmitter Crusoe.
Yeah.
So it's interesting to see those ideas come back around. NVIDIA seemed to have done well with Denver, and it's going to be interesting to see if these VISC guys can do much the same thing on their end.
All right, I think that's gonna wrap it up. It's 2:20 in the morning here, and you've got a family, so
you need some sleep.
Well, that probably too, but like, you know, I'm a student. I don't sleep anyway.
All right.
So thank you very much for agreeing to do this with me, Josh.
Yeah, not a problem. Thanks for inviting me. It was a lot of fun.
So this has been episode 1 of Tell Me More. I can't tell you who we've got coming up next because they haven't actually told me when they can do it yet. But once I know, you guys will know. Josh, do you want to tell people when they can find you?
Yeah, you can find me writing at pcper.com. I'm on Twitter for the time being. My username is Josh D. Walrath, WALRATH. You can find me in those two places. I'm usually quite vocal in both. And we have our PC Perspective podcast every Wednesday night that we stream live. I think that's 8 o'clock Mountain Time here in the U.S.
Yeah, it's like 1 or 2 a.m. here.
Yeah, it's pretty brutal for you.
Yeah, I usually catch the YouTube embed the next day.
But you can also find us on YouTube. So.
Yeah. So I am at mobile_dom on Twitter. You can find me at www.mobiletechtalk.co.uk. Again, I am the senior reviewer there. I tend to stick to mobile, but I do Chromebooks, smartwatches, and pretty much everything in between. So until next time, goodbye.